We're going to take a look at another example of how we're going to model a circuit with first order differential equations. So here we have a circuit, another voltage source. We're going to work with a series where we have an resistor R and a capacitance C connected in series to form this series circuit. So here's our R, here's our C. This is our plus for the battery, this is minus, this is a voltage source V, S. This is our direction of that current, therefore our polarities for the voltage across the resistor is here. We have the same current going through the resistor through the capacitor. That's a plus and a minus as well. So here we're going to use KVL for this circuit. So this is our let's say we start right here. This is a voltage rise. There's a voltage drop across our resistor, and there's a voltage drop across the capacitor. The sum of the voltage rise is equal to the sum of the voltage drops, and in this case the voltage rise is Vs. The voltage drops is across R, the resistor R, and the voltage across the capacitor C. We're going to form our differential equation here. Using Ohm's law, we know that this is IR, and for our capacitance we know it's Q over C. Notice we have an I and a Q. We want to reduce our number of variables, but we know that I is the first derivative of dq dt. So we'll replace I in this case with dq and dt plus q over c. So here you have a relationship that's a first order, and our dependent variable is charge. And we can calculate the current by taking the first derivative charge with respect to time. Let's put this in standard form, where we have dq dt plus 1 over RC times Q equals Vs divided by R, where we took this equation, rearranged it, and divide R on both sides, and this yields this relationship here. Now we can find the solution to this first order equation. Okay. Alright, so here we'll form our integration factor. Where we have E integral of 1 over RC dt, which is equal to e to the t over RC. This is our integration factor. And our solution can be formed based on our integration factor by forming this E t divided by RC, and our dependent variable is Q. And on the right side we have Vs over R times our integration factor T over RC, and that's our relationship. Again, when we take this derivative with respect to time, we get this equation on the left side. Okay? When we multiply that by the integration factor of this equation. Alright? So here, taking the integral on both sides of this equation, we have Et over RC times Q, and you integrate this is just Vs over R, and the 1 over RC becomes a RC in front, and this becomes Et over RC plus the integration constant. We'll call this integration constant C1. Okay, if we want to isolate Q on one side, so Q is equal to Vs, the R's cancel here and here, times C, E well, that's going to cancel out when you divide that out. So we're going to add plus C1 e to the minus t over RC. Now, assuming there's just zero charge across there, capacitor is equal to 0, so that's just Vs times C plus C1 e to the 0 RC, which is just 1, which implies that C1 equals negative Vs times C. Rewriting Q is equal to VSC plus negative VSC e to the minus t over RC. We can simplify that as VSC 1 minus e to the minus t over RC. So that's Q. Now we can get the current from here by taking the first derivative of Q, which will equal to, well, this is going to split up as here, so the first term of Q will equal 0, and the second term will just be VSC and divided by RC. We have a negative, but the negative in the exponent will cancel the negative that's outside here. So the C's cancel, so that leaves Vs over R, e to the minus t over RC. But that's equal to Vs over R e to the minus t over RC. And that's our expression for our current. Notice after 5 time constant, and the time constant in this case is RC, so after 5 time constants, this goes to 0. And if you take a look at the circuit here for the current, after a certain amount of time, the capacitor blocks all the current, and therefore the voltage across it, or the current through the capacitor and the resistor, will end up 0. And we've found that solution to be true with this equation when we solve this first order differential equation shown here. And our charge is governed by this expression here, and our time constant is governed here, which gives us an idea when the current will go to 0 once we know the value of R and C.